4. All right, this should be easy one. Prove that if you have this limit of mx plus b, okay, this can be anything, is just ma plus b. All right, so here assume m is not 0. Okay, so what we need to prove here. All right, so let's make some observations. All right, so this is f of x minus, this is our L. It's just mx plus b minus mx plus b again. So if we compute that one, b cancels. You can take m out and you get x, sorry, this is a, supposed to be m. Sorry. With m out, then this is just x minus a. All right, can you follow me? Hello?
Yes, you can, sir.
All right, up to this one. And if you would like to have, this should be less than delta, right? And this, the whole thing could be less than epsilon. So how we decide on the relation between delta and epsilon and delta, right? So then this should be over. Yeah. Okay. So the proof goes like this. Let epsilon be a positive number. We choose our delta to be epsilon over. Okay. Then if we assume x minus a is less than delta, which is equal to this, then, all right, so then just rewrite these observations. Absolute value, which is m times x minus a. All right, so with assumptions, this is less than m times, let's cancel. That's what we need. Okay, so this tells you that for linear equations, linear functions, you just plug in the x by a, plug in a to x, replace. Okay. All right. For 5, I'll prove this one. I'll let you do this one as exercise later. Okay. So this is almost exactly the same as this one. Square. We did square before. All right. Let's do this one. Yes, illustrations. 1 minus. Right. So just plug in 1 to this one to get 1/3. But how we prove this one? All right, so let's do the observations. Okay. Uh, Again, this is our f of x. This is our L. So this gives you 1 over x plus 2. And if you deal with the fractions, the additions or subtractions, then there's nothing you can do is what you call common denominator. All right. So with this common denominator, let's see what we have here. X. All right. So this is 3 minus x plus 2. All right. The common denominator. And what we have here, here you have the x minus 2. So 1 minus x. Okay. But 1 minus x is the same as this one. So here we have 3, sorry. Just write this as 3 times x plus 2. Okay. So from here we have x minus 1, right? Already here. But here we need to bound this. For this one. Need a bound, upper bound. Okay. So upper bound for this is, let's see, how to find upper bound. The thing here is, okay. So remember, last time I think in the tutorial, Kakemal mentioned that what if you find a bound for a fractions? If you want to find an upper bound, you can enlarge the numerator or make the denominator smaller. All right. So enlarge, smaller. So that's the idea. You can do uh, any one of these, or you can do both. Okay. Questions? Are you okay? Are you with me up to this point? Hello.
Yes, sir.
All right, so let's do this one. One is already a constant, so let's make this smaller. What is smaller than this one? Smaller than that one. Uh, let's see, this can be let's see. The thing is, this can be very going to 1. 1, 1. How to make this smaller than this one? Make it smaller. What is x minus 2? Smaller than this. Right? So then let's assume, just assume. So assume x minus 1 is less than, say again, 1/2. Okay, so again here, 1/2 and 3/2. Okay. And but we need now to make this smaller. So this is bigger than something. You see, now we need this is smaller. Make it smaller by what? Smaller is, take this is 1. Okay. So this is lower bound. Why lower bound? Because this in the denominator. Okay, so back to this one. So this is less than 1/3 times half. Okay, so this is 15. Okay. So get this upper bound. Okay, so this is lower bound for this in the denominator. Why we need lower bound? Because this in the denominator. Okay, but we need upper bound for this. All right. So let's okay, this is okay. So let's the proof now. Proof. Get epsilon positive, and you choose delta, the smaller than that 1/2, and epsilon over 2/15, which is what? 15 epsilon over 2. Okay, so the minimum. All right, so then let x is 1 less than delta. Okay. Then f of x minus L. L is, what is that thing? 1/3. X plus 2. So we kind of repeating these computations. Sorry, have to go back. Oh, okay. So this 1 there. Okay, so this one is less than delta. Okay, and delta is less than 15. Okay, so then this is less than All right, so this is less than what? This is less than 2 over 15. Okay, times this one is less than. There we go. Okay. In fact, you can show an easier version of this is this is number 7. Show that limit of x a 1 over x is just 1 over a. A for sure is not equal to 0. That's the issue. Okay. One more example here is um, a positive, a is non-negative in this case. Okay, so how to show this one? So our observations is this one. Okay, so then how we deal with this? All right, so how to deal with this is try to get rid of the square root. So how to get rid of square root? You sorry. The trig plus. So basically you multiply by 1. Okay. But with these multiplications, the value you have there. And here, okay. Yeah. We don't need the absolute value here because it's a positive. Okay. So we need an upper bound for this. Okay. Need upper bound. Okay. So in this case, upper bound for this turn out to be we need lower bound for the denominator. Okay. Upper bound for the whole thing, and when the whole thing's bigger, when the denominator smaller, right? And what is small? Because this is a negative, so this the whole thing supposedly. Okay, and that's what we need here. So this could be smaller than 1 over square root of a times x. Okay, so if you want to have this is less than epsilon, that should be epsilon over this means that, let's see, just right. Okay, so then the proof goes like this. See, this is repeating epsilon positive. So we choose our delta should be this one. So square root of a times epsilon. And you assume that x minus a is less than delta. Then rewrite the computations. Square root of x minus square root of a is, well, we have this one, x minus a. Okay, so this is smaller than, okay, and we assume this is less than delta. This is 1 over square root of a times delta is this. Cancel. There, let's make it. Okay. Questions? Another properties that I would like to show you without any proof is that suppose fx is L, limit x of g of x is M. Then 1. You can find the limit of the sum. Okay. The sum is L plus M. So here you compute the sum first and take the limit. Here, in order to do this, you compute the limit first. Compute L, compute M, and then sum. So this sum and then limit is the same as the limit and then sum. Okay. But that's the same as subtraction. Okay. And limit of multiplications. Okay. So it's the same as the product of the limit. So you multiply first and then take limit, the same as the find the limit first and then multiply. We have also for this one, for the ratio. But on one conditions that M cannot be 0. Okay, so another example. This is the same as this limit. Forgot this one. 1b, say. You multiply the f by a number k, and you can find limit here. It's all the same. K constant. Okay. So with these properties, then we can say that, well, take the 5 out and you find this limit. Okay, take 7 out This is a constant, okay? But we computed earlier. Then if you have this x cubed, then you just have, here you have constants is the same, right? So if this is f of x, this is f of 5. So in general, if you have a limit of polynomial, it is the same as substitutions. So let's say just general. If a p is a polynomial, okay, polynomial when x with powers, okay. So then this limit is the same as substitutions. Okay, so this is the thing that we derive from the definitions actually using these properties. Okay, so this is what I call the trivial part of the limit, when limit is the same as substitutions. Limit is same as substitutions. Easy case of limit. Okay, and derive through the definition of limit. All right, so that's the basic idea of the definition of limit, used for to prove basic things, and then we just use the basic things. Okay. Okay, let's now to see that when is limit is not the same as substitutions. Limit not the same as substitution. You cannot just substitute. Well, we learned that earlier, that you can do factorizations, cancel factors, and then those kind of things. Okay, and but what we want to show you is these properties, what we call a squeeze theorem. Okay, so squeeze theorem basically says that suppose you have a G is squeezed by G and H for X in some interval. Containing point A. So this is A, this is the interval. Some open. Okay. So then what happened here? Suppose also this is assumption 1. Assumption 2, this limit exists. And this limit sorry, m, both x's. Okay, so then the left and right. Okay, then this also true. Then limit of see, what did you call? This is what I should say something like this. This limit, if exists, okay. So if you have G is sandwiched between F and H, then the limit, if exists, also sandwiched between the limits here. Okay. And in particular, if L equals M, so that this limit is the same, then somehow the G gets squeezed over by L and M. Okay. Then it just gets squeezed by this. Okay. Okay. All right. So just a note here. We assume L and M exists, so the limit exists. If there's no limit, then there's a different case. Okay. Example. All right. So let's do this one here. Let's say find the limit of x getting to 0 just from the right. Okay. X square sine 1 over, say 1 over x. Okay. All right. So the remark here is that uh, we know this limit is 0 because this is polynomial squared and we compute this limit, just substitutions. But this limit, sine 1 over x, does not exist. Remember, this is the extreme oscillations. Okay. So then the product here, these properties, does now we cannot use this one, limit of x squared sine 1 over x equals limit x squared times limit sine 1 over x. Because this is 0, then this is incorrect. See? The limit of this is 0 anyway. But 0 times something that does not exist, that's questionable. And we'll show later that that's not true. So we cannot use this one. Okay. So even though the 0, the answer is correct, but this is not the way how you get the answer. Okay. We use the squeeze theorem. Use squeeze. Squeeze theorem. Let's see. All right, so let's see here. Let's do sine of 1 over x. All right, so sine over x is between let's see. Okay. Sine 1 over x is between -1 and 1, right? For x not 0. And so we get, since this is true, then multiply the whole thing by x squared. Okay, because x squared is non-negative, so because non-negative, then there we go. Okay, so this function, our f of x, is now squeezed between x squared and minus x squared. The thing here is that limit x goes to 0 positive of x squared is 0, same as minus x squared. So this, the limit of this exists and it's squeezed between 0 and 0. So that's 0. So this is the case when you have squeeze. So by squeeze theorem, x squared okay, so you squeeze in this case. Okay, questions? All right, any questions so far?
None yet, sir.
Not yet? All right, so this is the basic thing of a computing limit, right? So use those properties and squeeze also, and we'll derive some more properties using this one. Okay, so for trig functions, I would just mention that the this one, special trig limit. Okay, a special trig limit is this one. X when limit small, same as this one. uh, just write this. This is the same as x over sine x. This is give you 1. The another is tangent, also 1. And then the next is um, 0, 1 minus cosine over x. This is 0. Okay. Okay, we'll derive this using squeeze, but what does it mean? Okay, so what I would like to read is as this one here. Uh, if you write something like this, I would say this is small, but not equal 0, but not 0. Okay, just a small. Okay, so when we compute this thing, when x is small, you see that this is small. Sine x is also small because the graph looks like this one. Okay. X small. See, this is also small. Okay, so you dividing small by small. Okay, and the answer is, in this case, in this limit, is 1. All right, so what you say is that this small divided by small is comparable because they are almost the same. Okay, but here we go. 1 minus cosine x is not really 0 when x not, but this is small. This is small. But the ratio now is, now this is not really 0 in this case, in this context, because this is the limit. Okay? So this is also small number. Now the limit is 0, but this is small. When you take the limit out, then the small divided by small is small. Okay, so what it means is that, well, if you take small, something like this, which one, what can you say about A and B? Which one's smaller and which one's bigger? A over B is small. What can you say about A and B?
Well, both are small, right?
Uh, Not only smaller, but so in this case, A is much smaller than B. Like 10 and say million. Okay, 10 is much smaller than million. Okay, so that in that sense, A is smaller. So you see that if this is the case, 1 minus cosine x is small when x is small, but this is much smaller than x. Okay. So this is how you did this one. All right, so I will end it here. 1 over x cosine of x is much smaller than x. Okay, so limit provides you with a kind of, if in biology you know a microscope here, we have limits. So you're observing small things. You're observing whether this microbes is larger or smaller than other microbes. Okay, virus and bacteria, which is smaller. Okay, so this could give you a microscope point of view using limit actually. All right. I think in the tutorial session later, I will take about 20 minutes to uh, at least explain this thing, these special trig limits. So then in the tutorial, you can, and session, you can exercise with the other more general trig limits. All right. I'll stop the records now. Questions?